Hey everyone, welcome back. Today we are dealing with the fourth topic of our syllabus, which is chemical bonding. And before we start, I just want to let you guys know that this video is the first part in a three-part series I'm making on this topic. After that, I will upload its following worksheet just as I did for the third one. And I will try my best to combine topic 1 and 2 as well so that we get more practice on that. Okay, so without any other delays, I'm going to start. Just a quick reminder to drop a like on the video if you really like it. I will be putting timestamps in the description as usual. And let's go. So, chemical bonding. You already probably know from IGs there's ionic bonding, there's covalent bonding, metallic bonding. But in chemical bonding for A level, we first need to establish a few fundamental terms. So we have electronegativity, which is defined as the ability of an atom to attract electrons towards itself. What this means is an atom, because it often has, you see how it has a positive center? That center can usually attract other electrons, not just its electrons, but electrons from other atoms towards itself. That's what electronegativity is. It's the ability of that atom to attract electrons towards itself. So it's like a trait of that atom. And we have factors influencing this trait. Nuclear charge, which is very obvious. If you have a greater nuclear charge, which means a more positive center, as in more protons in your nucleus, then you'll be able to attract more electrons, so the greater the electronegativity. Then we have atomic radius. The larger the atomic radius, the lower the electronegativity, which also makes sense because if we look back to shielding, shielding is when the electrons in the shell around the nucleus protect the outer ones from feeling that entire nuclear charge. They take it upon themselves. So if the atomic radius is sorry, I just explained the third point. I'm sorry. The atomic radius is actually related to shielding. They go kind of hand in hand because the more large atomic radius means that basically you have more shells in the atom. So the atomic radius, if it's larger, it means that the nuclear charge is not really going to be able to get to the end of that atom, to the valence shell. So it won't be able to attract other electrons towards itself, which is why the electronegativity is lower for both atomic radius and shielding effect. And electronegativity increases across a period and decreases down a group. Now, why would this be the case? Well, this is our atom. I just drew a simple atom as an example. So across a period, what we have is the number of shells remain the same. So if there's one shell across the period, it's going to be one shell only. But then the number of electrons are going to increase. So if we have the first element of that shell, one electron, the second one would have two electrons, then third, fourth, and so on. So the number of electrons would increase, and hence electronegativity would increase. Since once the number of electrons increases, they will be more attracted towards this nucleus. Nucleus was able to pull these electrons further towards itself, so its atomic radius decreases. We know that across a period atomic radius decreases. So if it decreases, then the smaller the atomic radius, the larger the electronegativity. Hence, in the periodic table, fluorine is the most electronegative. So As you can see here, fluorine is the most electronegative element since it's sitting at period 2, and it's the, well, seventh element of that period. We don't count, um sorry, we don't count neon as being electronegative since it's a noble gas, so it's not really counted in that. But fluorine is our most electronegative element. Also, fluorine has the ability that it can take in one electron as a result of ionic bonding. So if fluorine needs to bond with any of these metals, it would just need one of their electrons. And the ability of it to get that one electron is extremely high because of how small it is. That's for the um, increases across a period. Decreases down a group, that's because of the atomic radius. The atomic radius decreases down, sorry, increases down a group. The atoms get larger and larger as more electron shells are added. So the ability of that atom to attract electrons becomes way less. Hence, the electronegativity would decrease. The way I usually remember these trends is to remember that fluorine is the most electronegative element you can have. And once you just remember that fact and you see your periodic table, fluorine is in the corner here, you can immediately tell that, oh, fluorine is at the extreme right and it's at the top. So that means as the periodic table goes from left to right, it gets more electronegative, and from bottom to top also. That's usually how I remember the trends, because I don't really like memorizing the trends. I would just memorize a simple fact and then from there I derive all the trends. But if that doesn't work for you, you can just remember the trend. Okay, so we're done with electronegativity. Now we're just going to tackle the three different types of bonding, and that will be it for the part one, because otherwise I would have to go much further, and that will take up way too much time. I want this to be a short and concise video so that it doesn't take up much time. So we have ionic bonding. Ionic bonding is defined as the electrostatic attraction between oppositely charged ions. So a negatively charged ion and a positively charged ion, same as in IGCSE. So over here I've drawn diagrams of two simple ionic two compounds that are ionically bonded. So we have sodium here and chlorine here. Normally you're supposed to draw the valence electron shell. So as you can see, to demonstrate that chlorine took one electron from the sodium, I actually drew the shell of sodium so that you can see that it's the x's that came here. Otherwise, you can just leave sodium as it is. You don't have to draw the shell, because technically you've already taken away the electron. It's allowed to not draw anything for the metal, especially if it has one electron in its valence shell. So this is just how you draw it. Sodium is actually much smaller. The sodium ion is much smaller than the chlorine ion. So I kind of drew it to demonstrate how it would look like. Also, sodium chloride is an it has a cubic lattice shape. So its structure sort of looks like a cube where, hold on, I don't know if I can draw this one. Okay, so it sort of looks like this cube where these are the atoms and they're just bonded to one another. That's sort of how it looks like. Each chlorine is connected to a sodium and so on. Because sodium chloride is just normal table salt. So, and table salt is often found in like crystals. So these are like sodium chloride crystals. The larger dots that I have are the chlorine ones, and then the smaller one is the sodium. That's kind of how its structure would look like. And that is why I've drawn this chlorine ion a lot bigger than the sodium one. But yeah, it's just as simple as it was in IGs. You draw the valence shell and then the square brackets around it, and then its charge. For sodium, it's +1 and chlorine is -1. You don't write the 1, but if it's -2 or +2, you write the 2. Okay, and then we have magnesium oxide. Magnesium oxide, similar to the sodium one, oxygen needs two valence electrons to complete its valence shell so that it can achieve that noble gas configuration. Magnesium needs to let go of its two electrons and its valence shell so that it can also achieve a noble gas configuration. So this works perfectly, and one magnesium atom would need one oxygen atom. However, if we had to make sodium oxide, because sodium has just one valence electron, you would need two of those sodium atoms for every one oxygen atom. So that would be sodium oxide. So, yes, that is just how simple it is. Ionic bonding, the diagrams are the same as they were in IG, so I won't really go any further. Then we have metallic bonding. Again, similar. Metallic bonding is defined as the electrostatic attraction between positive metal ions and delocalized electrons. What do we mean by delocalized electrons? So, in I've drawn this metal rod here, and the metal is just M. So that doesn't represent any element if you were thinking anything. So over here, M, basically, you know how metals have all their properties, they're really hard. They are, sorry, they're really hard. They have high melting points, high densities, and also they're ductile and malleable. All of that comes from the way this entire thing is structured. So, lattice of positive ions in a sea of electrons. That's the way you describe its structure. Describing a structure is defined as the lattice of that structure. So, here the metal ions are actually separated from their electrons. So, those ions are always positive. Metal ions are always positive. So, they lose their electrons, and those electrons are arranged around them in like a C type of structure. So like there's a sea of electrons, and then you have your positive ions. They sort of alternate between these electrons, and this provides it with a lot of it makes it a lot more tough. It makes the metal hard, it makes it malleable, which means that you can easily bend this metal by like striking a hammer or something. And then ductile, it just means that the way it's arranged, sort of in layer like, you can arrange the layers and everything. And delocalized means that the electrons have been removed from their atoms and they're just like kind of free and moving around, which is why we often say it's a sea of electrons, because that's how their movement, I wouldn't say movement because they're kind of rigid, but it's how their arrangement is described. And this gives metals some of their properties, which I've already explained. So that's for metallic bonding. Now we have covalent and coordinate bonding. You're probably familiar with covalent bonding. I'll just explain that briefly. So, covalent bonding is defined as the electrostatic attraction between the nuclei of two atoms and a shared pair of electrons between them. So ionic bonding is the transfer of electrons from the metal to the non-metal, but this one is two non-metals basically sharing a pair of electrons. In the further examples I'll give, you see that it's not always all non-metals. So just a few basic examples to get us started. We have water as our first one. So in water you have which is H2O, you have two hydrogens, one oxygen. This is how you would draw the simplified structure of the molecule. You usually draw these two unbonded, or these two pairs of electrons that are not used in bonding, as lone pairs. So they're sitting alone outside the oxygen here. So you draw them individually. You always have to draw lone pairs. It's very necessary. It helps to just it helps in the later part of this chapter, which I will explain. Well, basically it kind of helps you to determine the shape of the molecule. I've drawn the shapes here, but you will need to draw the lone pairs when you're writing the molecule, so that you know what shape to expect from that molecule. So in water, the hydrogen has one electron and oxygen needs two, so it takes two electrons from two hydrogens to complete its octet. An octet is basically just a shell with 8 electrons. So ammonia, which is NH3, the nitrogen has a lone pair of electrons, so we have to draw that. Then it bonds with three hydrogen atoms since it needs three electrons to complete its octet. And then the nitrogen molecule. Nitrogen molecule has a triple bond. A triple bond means three pairs of electrons are shared between the two atoms. So that is what is shown here. Since every nitrogen atom needs three electrons in its valence shell so that it can complete its octet. Okay, those are the simple examples. These are some exceptions to that rule. So in period 3, we have two exceptions, which are sulfur and phosphorus. These two elements can expand their octet. So they are not limited to 3 electrons. Sorry, 8 electrons in their valence shell. So here we have SF6, which means a sulfur atom can take up to 6 fluorine atoms. You already know that fluorine needs one valence electron, and sulfur has 6 of those. So it can donate all of its 6 electrons to 6 fluorine atoms. But then in the process, its octet gets expanded. So it has now 12 electrons in its octet instead of 8. For PCl5, the phosphorus atom has 5 valence electrons, so it can bond with 5 chlorine atoms to give those 5 to share those 5 valence electrons. So chlorine completes its octet, but phosphorus expands it by 2 electrons, so it has 10 electrons in its octet. Then we have sulfur dioxide. I can't believe I wrote this. Sulfur dioxide. So the sulfur atom, again, it has 5 electrons, but it double bonds with 2 oxygen atoms so that they can complete their octet, and it expands it in the process. And this is sort of an explanation for that. Sulfur has 6 valence electrons, but it has 4 electrons in its 3p orbital. And then phosphorus has 5 valence electrons and it has 3 available in its 3p3 orbital. What can happen is that since it already has a third shell, right, its 3D orbital is empty. So this 3D orbital can get more electrons if it has to. So technically, to complete its octet, it can just keep on expanding the number of electrons it takes in because both of their 3D orbitals are empty. Hence, they can take in more and more. These two, however, are the only exceptions you need to know for period 3. Alright, and we come to the last part of today's topic. Sometimes coordinate bonding occurs. What is coordinate bonding? It's basically, you see how covalent bonding is when both atoms share, right? Coordinate bonding is when one atom gets a little bit greedy and takes both electrons for themselves. And yes, those both electrons do not belong to that atom. It's a selfish atom. So it's a type of covalent bonding in which both of the electrons in the pair used for bonding come from the same atom. As I said, a very selfish atom. So basically what we have is this ammonium ion forming from the base ammonia. How it forms is the base accepts a proton. So a proton in this case is a hydrogen ion. This is our hydrogen ion. And ammonia is neutral. So when it accepts this ion, it becomes positively charged. So we have our square brackets and the positive charge. Now, nitrogen has a lone pair of electrons when it forms ammonia. So this lone pair of electrons is sort of given to hydrogen to form a coordinate bond. Coordinate bonds are also called dative bonds. So nitrogen will share its electrons with the hydrogen here. When you need to write this in like a simple form, what you usually do is do the ammonia as usual, and then because those two lone pairs are going to be donated, we draw an arrow, which means that there's a lone pair here, but it was given to another atom. That's how you draw it. Another example here, we have aluminium chloride. Now we can have AlCl3, but then I believe, if I'm not wrong, I could be wrong, but when AlCl3 is sort of heated, or I believe when it's like compressed, it forms Al2Cl6, which is also aluminium chloride. So this is the molecule that undergoes dative bonding, not the AlCl3. So for this one, the chlorine, now aluminium has 3 valence electrons, so they will share with 3 chlorine atoms normally. And then chlorine has 2 electrons, like a pair of electrons which it can share with aluminium so that aluminium can get its octet. And that chlorine atom will get the valence electron it needs from the other aluminium atom. And then the same for goes for this chlorine atom. So it sort of looks like this. One chlorine atom donates to one aluminium atom, and another chlorine atom donates to another one, so that every atom can complete its octet. And yeah, that's basically what coordinate bonding is all about. And with that being said, I've come to the end of this part of the chapter. I hope you guys liked the video. I hope it was short enough to keep it you guys engaged. And please like the video, subscribe to my channel for more updates. I will be updating regularly. And yeah, I hope to see you guys soon. If you do have further questions, please leave them in the comments. I will address all of your concerns. And thank you guys for listening. Bye.